What is up, everybody? My name is Frank, and this is the Python Programming video log. Today, I'm doing a Watch Me Write video on how to draw a 3D cube without any external libraries, just 100% pure JavaScript from scratch. I'm going to write every single line of JavaScript in this video for you to see, so stick around if you want to know how to do a 3D cube example in the browser. Alright, so to get started, I've already written all the HTML and CSS for this project, and basically, I'm just going to get right to the JavaScript, so hopefully you guys are okay with the HTML and stuff. But let's get started by just saying var context equals document dot query selector canvas, and we're going to get the 2D context with get context 2D, and that's going to get us a drawing context. Now, the next thing I'm going to do is create a game loop, so I'm just going to say function loop, and that's going to be the function that I'm going to call on every frame of animation. To perpetuate the game loop, I'm going to use window.request animation frame, and I'm going to hand in the loop function itself, and then to actually start the game loop off, I'm just going to call loop just like that. Inside of here, I'm going to need to get the width and height of my browser window, so I'm going to say var height equals document element client height, and var width equals document element client width. And then I'm going to go ahead and I'm going to fill the canvas, so I'm just going to say context.fill style equals, let's test it with some green, so 008000, context.fill rect 00, and the width and height variables we just made, so height, there we go. And also what I'm going to have to do is resize the canvas, so I'm going to say context.canvas.height equals height, context.canvas.width equals width, and that's going to just resize my canvas on every frame of animation. So let's see if I got that much right. Alright, so I have a nice green canvas background, and when I resize my window, the canvas resizes on every frame of animation on width and height. So now I have a basic canvas set up, and I can start programming the actual cool stuff. So let's go up to the top and create some classes. I'm going to need, let's see, const point2d equals function x, y are going to be parameters for point2d. The reason I need point2d is because I'm going to project my 3D points onto a 2D screen. So I'm actually going to need 2D points to represent my 3D objects after those 3D points are projected. So real simple, just some point classes. This.x equals x, this.y equals y, and actually I can collapse all this because it's really simple. So I'm just going to put it all on one line for readability, or size purposes. And then const point 3d equals function x, y, z. This dot x equals x, this dot y equals y, and this dot z equals z. And it's basically just going to be a point placeholder. So it's just going to hold 3 values. Then I'm going to actually create my cube, so const cube equals function, and I'm going to have x, y, and z again, and also I'm going to have size. So x, y, and z for the cube is going to be, or are going to be, the center point of the cube. So I'm just going to call point3d.call this, comma, x, y, z, and now the cube class is going to inherit the x, y, and z values from point. And now I can go ahead and do two things. The first thing I have to do is define my vertices. So I'm going to say this dot vertices equals, and this is going to be long, so I'm probably going to fast forward through this, but basically I'm going to just make a whole bunch of 3D points. Okay, so these are going to be all the points in the cube. So this would be the front point. The point would be at the top left corner of the face of the cube, the front face of the cube, and it would be on the front face of the cube because I'm subtracting size from the center Z, or the depth axis of the cube. So, and then I have the top left here is the first point, top right, bottom right of the front face, bottom left of the front face, and then I do the same direction on the back face, and I'm just creating points for each of the 8 corners of the cube. So now I'm going to do the faces. Okay, so the faces actually correspond to each side of the cube. So each side of the cube is going to have 4 points. So this is going to be the front face. So the front face of my cube is going to refer to these 4 points, 0 through 3. So at index 0 is going to be this point. Index 1 is going to be this point, then 2 and 3. So basically, each face points to some points in this vertices array. So all of these, and this is something important to note, all of these are going to order points in clockwise order. So every face is going to have the points of the face ordered in clockwise order. That's why these are kind of at strange, in a strange order. 1, 5, 6, 2, that's a strange order, but what it is it's the clockwise ordering of the points for that face. And that's very important because we're going to have to determine what the surface normal of a face is in order to do backface culling. So now we have a basic cube, and what I'm going to do is I'm going to go ahead and I'm going to come down here and I'm going to create a cube. So I'm just going to say var cube equals new cube, and it's going to be at 0, 0, so x and y are going to be 0, and z is going to be at a depth of, let's just say for now, let's say 300. Oh, yeah, 300, and the size is going to be 25. And actually, because I'm using size to position the points of my cube around the center of the cube, what I'm going to want to do is I'm going to multiply size by 0.5. Size basically represents the width, height, and depth of the cube. So because I'm subtracting size from the center of the cube, I'm going to want to cut it in half. So that's all that's doing right there, and that's going to keep the cube at the width, height, and depth the same size, and the appropriate size that I actually specify. So now let's go ahead and draw this cube. Actually, first let's test it and see if there are any errors. So I refreshed, and there are no errors in the console, so now I know that my cube code is at least syntactically correct. So now let's go ahead and draw this thing. So I'm just going to say context.fill style. Actually, I'm not going to use a fill style. Context.stroke style equals black. And then what I'm going to have to do is I'm going to have to loop through all the faces of the cube. So I'm going to say for let index equal cube dot vertices dot length minus 1, index is less than or greater than -1, minus minus index, and let face equal cube. Oh, actually, I'm looping through faces, not vertices, my bad. So we're going to do cube.faces.length, and I'm going to say face equals cube.faces index, and that's going to give me the appropriate face. And now what I'm going to do is I'm going to draw each point, or I'm going to draw a line between the points. So I'm going to say context.begin path, context.move to face 0. But I'm actually going to have to use the cube's vertices, so I'm just going to say cube.vertices at face 0.x, and then cube.vertices at face 0.y. And then I'm going to use basically the same format to do the line twos to the other points in the face. So I'm going to say context.line2 Control V, and I'm going to go ahead and increment up the face. So now we're going to draw the next face. Or not the next face, but the next point in the face. And there are 4 points in the face altogether. So let's copy that. Control V, Control V. That's going to align to the next 2 points. That's going to be point 2. That's going to be point 3. We're going to close the path back to the point that we moved to, and we're going to context.stroke, and that is going to draw our lines. And also, I'm going to get rid of the green, and I'm just going to make it white. So let's see what we have. Okay, we have this cube. It's not a cube yet because it's not 3D projected to 2D, but it's basically a 25 by 25 pixel square in the upper left corner of our screen. So now what I'm going to do is I'm going to project the cube. So I'm going to write a function called project, and that's just going to be function project. It's going to take vertices 3D, or actually let's just say points 3D, and width and height. And width and height are going to be the width and height of the browser window. So we're just going to take that from the width and height variables that we created inside of the game loop. So the first thing we're going to do is say var points 2D, and this is going to be an array that holds all of our 2D projected points. We're going to make that a new array that is the same size as points 3D.length, because we're going to create a 2D point for every 3D point we encounter in that array. So then I'm going to say let p equal points 3D index, and then I'm going to go ahead, actually I'm going to have to loop through all the points in points 3D, so I'm going to say for let index equal points 3D dot length minus 1 index is greater than -1 minus minus index. I'm going to move this inside of the loop. And then I'm going to do the projections. So let x equal p dot x times focal length. Now focal length is important, and I'm actually going to define it out here. Var focal length. Focal length I'm going to set equal to 200. What focal length is you have a point for your camera inside of your game world. So wherever the camera is located, it's going to be located at a 3-dimensional point. Focal length is the distance from that camera point to the screen, so to speak, that you're projecting onto. So imagine, if you will, there is a 3D point which represents the camera position, and then there is the viewing screen that you're going to see all of your 2D projected points on, and that's going to be where you render all of your graphics. So this is going to be the distance or the depth from your camera position to the 2-dimensional screen that all of your points are going to be projected onto. So our focal length is going to be 200, and we can increase that or decrease that depending on how narrow or wide we want our field of view to be. So I'm going to go ahead and define the projected x value. So that's going to be p.x multiplied by focal length divided by p.z. And that's it. Pretty simple. Let's see here. Let y equal p dot y times same thing, focal length divided by p dot z. And we're also going to go ahead and add a translation value on there in a second, but first I'm going to just put this new projected point into the points 2D array. So points 2D at the index we're looping over right now equals a new point 2D, and that's going to have the values x and y in it. So this is where we're actually going to use the 2D point. So right now, if I were to plug these points into my drawing function that draws the cube, what would happen is I would still get a cube drawn up here in the corner, and I don't want that. So what I'm going to do is I'm going to translate this over by half of the screen width and half of the screen height. So I'm just going to say plus width multiplied by 0.5 and for y I'm going to say plus height times 0.5. And I'm not sure if I have any syntax errors yet, but I'm going to test this in a second. But first what we have to do is actually use this function and project our vertices. So I'm going to come down here and I'm going to say var vertices equals project cube dot vertices and width and height. So now I have an array of vertices that are projected in 2D, and that's what I'm going to use to draw instead of the cube's actual 3D vertices. So I'm just going to get rid of cube dot in front of cube, or in front of the vertices there, and now this value is equal to this. So when I save and I refresh, hopefully we don't get any syntax errors, but we do, of course. Points 2D is not defined. Okay, so I forgot to return up here. I forgot to return this. So all I have to do is come down here and say return points 2D. And also I have to change the variable name point2D to points 2D because that's actually what I want to do. So now let's refresh and see what we get. We get this very tiny cube in the middle of the screen, and I think instead of that very tiny cube, we're going to increase the size of it. So let's go to 50. Okay, and now we're actually seeing some projection going on here. So let's bring this a little bit closer to, let's say, to 50. I'm going to save. And I'm going to make this actually a lot bigger. So let's make this 200. Okay, that's probably too close. So let's bring this over here. Let's make this 400. Okay, that's pretty good, I think. Okay, so as you can see, now we have some depth. This smaller square represents the back face of the cube. This would be the left side of the cube, the top of the cube, the bottom of the cube, and the right side of the cube. And this big square in the foreground is going to be the face of the cube. Right now it's totally transparent. I'm only drawing the lines between the points of the corners. But basically with this formula, we have projected our 3D points onto the 2D surface, and that's why it looks like this. So now what I'm going to have to do to make this a little more interesting is rotate the cube. So I'm going to come back up to the cube class right here, and I'm going to define some rotation functions inside of the prototype of the cube. So I'm going to say cube.prototype equals an object literal, and I'm going to go inside and I'm going to make the functions rotate x and rotate y. So rotate x function, it's going to take a radian value. So radian, that's going to be the angle to rotate by, and then rotate y is also going to be a function, takes a radian value, and that's not going to have a semicolon. Okay, so let's start on rotate x first. So to rotate on the x-axis, what you have to do is you have to convert this radian from an angle into a Cartesian vector coordinate, or vector direction, so, or vector length. But it has a direction because it's a vector. So basically what I'm going to do is I'm going to say var cosine equals math.cosine radian. And basically what math.cosine does is it gets a x value of a vector from an angle. So it converts polar coordinates into Cartesian coordinates for the x-axis. Now I'm going to use var sine, and I'm going to set sine equal to math.sin or math.sine radian. And now I'm actually going to loop through all the points, and I'm going to rotate them. So let index equal this dot vertices dot length minus 1. Index is greater than -1 minus index. Inside, I'm going to say let p equal this dot vertices index. I'm going to come down. I'm going to say let y equal p dot y multiplied by cosine minus p dot z multiplied by sine. Let z equal p dot y multiplied by sine plus p dot z multiplied by cosine. Cool. So let's actually go ahead, I have to set those values to the points values. So p dot y equals y, p dot z equals z. Let's actually test the rotate x function right now and see what happens. So I'm going to save that. Probably going to get an error, but maybe not. We'll see. Let's go ahead and just say cube dot rotate x and put in a very small value. So 0.01. And let's see what happens when I refresh. Oh, okay. So the problem here is I did not translate my points to the center. So what I have to do is I'm going to have to go ahead and subtract this dot x, which is the center point, the center x value of my cube. Oh, and I'm actually in the wrong spot, so let's not do it there. Let's actually go to the right function, which is rotate x, and that's going to be equal to p dot y minus this dot y instead of just p dot y. P dot y minus this dot y, and same thing for p dot z. We're going to do p dot z minus this dot z, and same thing here, p dot z minus this dot z, and this is just going to be equal to now y plus this dot y, and that's going to translate it back after we do the, or after we get the rotation coordinates, this dot z, and we're just going to add that back. So now let's see what happens. Okay, now it's actually rotating around its x-axis. So the x-axis goes from left to right on the screen, or from right to left, depending on how you want to look at it. But basically, imagine that axis as a pole just running through the center of each side of our cube, through the left and right sides of our cube, and it's kind of spinning like a rotisserie chicken on that axis. So that's why we're getting rotation. It's kind of rotating from top to bottom, but it's actually rotating around the x-axis. So now let's go ahead and do the z, or the y-axis rather, with rotate y. And actually what I'm going to do is I'm going to come in here and I'm going to copy all this. Copy. I'm going to come in, paste it, and just change some values around. So probably going to fast forward through this. Okay, so I changed some things there, and basically when you're rotating around the y-axis, you're going to make modifications to x and z. When you're rotating around the x-axis, you're going to make modifications to y and z. So the axis you're rotating around, you're not going to make any changes to, but you're going to make changes to points in terms of the other two axes that you are not rotating around. So when you're rotating around x, you're going to modify y and z. When you're rotating around y, you're going to modify x and z, and when you're rotating around z, you're going to modify x and y. So there's some cool symmetry there that you may have noticed. Now I'm going to come down here and I'm going to do cube dot rotate y. I'm just going to say 0.01 again, and let's see what happens. Actually, let's get rid of cube dot rotate x for now and see what happens. All right, so now we're rotating around the y-axis. The pole, imagine, is running through the top and bottom of the center of the cube, and it's just spinning on that axis right there. So now when I bring back in cube.rotate x, we're going to get some rotation. And actually, let me make that negative and see what happens there. Nope, that's not what I want to be negative. I'm going to make the y-axis negative, and the reason for that is because the y-axis is actually inverted for JavaScript. So y, if you know your regular Cartesian quadrants, you have this being the top right quadrant and y increases. So the formula is backwards. I guess I could have adjusted it in the formula, which would probably be a better solution, but for JavaScript, this would be the lower right quadrant of that chart, and so y increases as you go down and x increases as you go right. But normally in math, y decreases as you go up from the bottom and x increases as you go to the right. So Just have to invert Y there to get things to rotate the way that you would expect them to. Okay, so now that we have rotation down, what I'm going to do is I'm going to go ahead and do some backface culling. But before I do that, I'm going to show you why there's even a need to do backface culling at all. So the first thing I'm going to do is I'm going to set a fill style for the cube. So I'm going to say context.fill style equals, let's go for some blue. So 80 full 0. That's going to be a nice blue color. And I'm going to, instead of drawing lines, I'm going to go ahead and fill in the faces. So context dot, actually I don't have to do anything there really. I just have to, instead of stroke, I just have to say fill, context dot fill. Cool. So now let's refresh, and I have my cube, and it looks fine, but let's go ahead and add stroke back in there. Context dot stroke, and what we're going to see is our faces are not really drawing in a Z-ordered fashion. Any face of the cube can be drawn in any Z order. So what you see is a kind of a mangled up cube. The faces are occluding each other, and it does not look, they're not occluding each other the right way. The faces that are closest to you can be drawn behind faces that are actually in the distance, and that's why you're looking at something that looks kind of mangled up and weird. But it's actually doing everything it's supposed to. We just have to cull out all the back faces. This way we don't draw them over top of our forward faces. So let's go ahead and do that. Where that's going to happen is inside of the loop right here. So what I'm going to do is, as I'm looping over for each face, I'm just going to go ahead and add some extra values. I'm going to say let P1 equal cube.vertices face 0. And by the way, now we're using the cube's actual 3D vertices. We're no longer going to be using the 2D projected vertices that we get right here from the project function. We're actually going to want to use the 3D vertices. And the reason is because we're going to have to get the surface normal of each face of the cube in order to determine whether or not the face is pointing towards us or away from us. If it's pointing away, like the back face of the cube would be, then we know that it's a back-facing plane and we shouldn't draw it. So for the sides, they're facing perpendicular directly out to the sides. We wouldn't want to draw those either, because technically the way they're projected, it's going to just be pointing away from us. So anything that's pointing away, we're going to cull. Anything that's pointing towards us, we're going to draw. So to do that, we're going to have to get 3 points from each face. We're going to have to get 2 vectors from those points, but before we get the vectors, let's get the rest of the points. Let P2 equal cube.vertices face 1. Let P3 equal cube.vertices face 2. And now we can get our vectors. So let V1 equal new point 3D, P2.x minus P1.x, P2.y minus P1.y, and P2.z minus P1.z. So how you get a vector is, if you get a vector between 2 points, what you're going to do is subtract the second point from the first point, and that's going to give you a vector that faces from the first point to the second point. So we're going to get 2 vectors using all 3 of those points. So let V2 equal new point 3D, and it's just going to be the same kind of thing, only P3.x minus P1.x, P3.y minus P1.y, and P3.z minus P1.z. So now we have our vectors, and the last thing we have to do is get our surface normal. So let's go ahead and say let n, that's going to stand for normal, let n equal new point 3D. And this is where it's going to get confusing, because in order to get the surface normal of a plane, not only do you have to get 2 vectors that represent vectors on the plane, you're also going to have to get the cross product of those 2 vectors, which is going to represent the normal for that plane. And depending on the winding of your points, and that comes back to where we actually define the vertices of our cube and the faces of our cube. So if we ordered these properly and they're in clockwise order, if the faces are ordering the points in clockwise order or counterclockwise order consistently, our normal is going to face consistently off of one side of the face. If we're just ordering our points clockwise or counterclockwise at random for each face, then we're going to have our normals being very inconsistent, and we're not going to be able to tell which face is facing us and which face is facing away from us. So let's just do the cross product and see what happens here, see if I got my code right. It's very easy to make errors when coding this kind of math with all these variables that look the same. So for the x value of our normal, we're going to do v1.y multiplied by v2.z. And yes, I have this written down. I'm reading off a phone right now. So minus v1.z multiplied by v2.y. That's going to be the x value. For the y value, we're going to do v1.z times v2.x minus v1.x times v2.z. And then for the z value, we're going to do v1.x multiplied by v2.y minus v1.y times v2.x. And if you notice again, there's that symmetry, just like there was for rotation. For the x value of our normal, we're going to work with the y and z coordinates. So the opposite, or the coordinates that are not the axis we're actually interested in. So for x, we're going to do y and z. For y, we're going to do z and x. And for z, we're going to do x and y. So hopefully I coded that the right way. And now it's a simple if statement. If, and we're going to put all of our drawing code for each face inside of this if statement, and we're just going to check to see if the normal of each face is pointing towards 0, 0, which is going to be where our camera is residing, our theoretical camera that we didn't actually make an object for, but it is residing at 0, 0, 0, 0, 0 actually on the x, y, and z axes. So now what I'm going to do is I'm going to just say if P1, which is going to be the first point that we got here, so this is going to be just a point in our plane, or in our face. P1 is just a point in our face. Could be any point. I could use P2 or P3. Just has to be a point inside the plane of the face. So I'm just going to say 0 minus P1, but instead of doing 0 minus P1, I'm just going to do negative P1 dot x multiplied by n dot x. And what I'm doing now is I'm getting the dot product of the vector from the camera to any point on the surface or the face that we're inspecting here. So 0, 0, 0 is going to be our origin. It's also going to be our camera location. So I'm going to do that minus any point on the plane multiplied by the corresponding coordinate of our normal, and I'm going to just add that to the other corresponding coordinates of the normal. So I'm going to do negative p1 dot y times n dot y plus negative p1 dot z times n dot z. And I'm going to test to see if that is greater than or equal to 0, and if it is, then I'm going to draw. And I might have to come back and adjust this, but I'm pretty sure that's the right way to do it. So now let's test to see if I'm culling things properly with just rotate x. And actually what I'm doing is I have it backwards. It looks like what I'm doing is I'm culling all the front facing faces, and what I should be doing is culling the back faces. So I'm just going to reverse this real simply, just go like that and refresh. Alright, so now I'm only culling the back faces, and what I have is a very nice looking 3D cube. So let's go ahead and add in the rotation for y. Save. Cool. Alright, so that is a rotating 3D cube. So now let's do one more thing to make this a little bit more interactive. What I'm going to do is I'm going to come down to the very bottom, and I'm just going to say window.add event listener, click, comma, I'm going to make an arrow function. And I'm just going to say I'm going to create a value here. I'm going to say pointer.x equals event.pageX. Pointer.y equals event.pageY. And I'm going to say minus width. And I haven't actually moved these values out yet, but minus height times 0.5. And what I'm actually doing here is I am making it so I can click on the screen to rotate my cube in a direction that I click, just to make it an interactive example. And I'm going to come up here. I'm going to have to declare the height and width variables outside of the loop here. So I'm just going to copy this. I'm going to bring it outside of the loop. Paste those. Get rid of these vars here. This way we're not redeclaring these for no reason. And then I'm also going to have to come up here and I'm going to have to declare a value for pointer. Pointer equals new point to D 0, 0. If I come down here, I've got pointer.x, pointer.y. So now I'm going to come up here and I'm just going to say, right before I draw my faces, I'm going to go ahead and I'm going to say pointer.x times 0.001, pointer.y times 0.001. Let's refresh and let's see what happens when I click. Well, I have to probably make this a lot less to make it actually look reasonable. That's probably too far. Let's take one of those zeros out of there. A lot of this stuff is just trial and error to get it to look right. Okay, so I'm going to make this negative pointer.y to flip that y-axis. And it looks like what I need to do here is actually just flip these entirely. So I'm going to do y, and I'm going to do x. I might have to move that around, but basically I'm just trying to get this right here. I want it to move towards the mouse whenever I click, and it does. So everything looks great. I think one last thing I'm going to do is I'm going to come in here, and I'm going to make the stroke style white, just to make that cube look a little bit better. I think that probably looks a little bit cooler. But there you have it, a 3D cube. So hopefully now you guys know how to draw a 3D cube and do backface, culling, and rotation in pure JavaScript. If you have any comments or questions, please leave them in the comments section. I'll try to get to them as soon as possible. Suggestions are definitely welcome. If you learned anything in this video, of course leave a like, and if you want to watch more videos, go ahead and subscribe. And I'll see you guys in the next video.